Alright, hello everyone, my name is Zach, and in today's video we are going to be going over a cooling system problem, alright? And there is a lot of construction going on outside my dorm right now, so I do apologize for the noise you'll be hearing throughout the video. I'll try my best to speak as loudly as I can. Hopefully you guys will be able to hear me throughout. And so we're going to go ahead and dive into the whiteboard. Now here, I have the problem that we're going to be looking up, drawn up, the real world of what it would actually look like in real life. So basically what we have going on here is we have this reactor right here, and within this we are going to be having a reaction going on that is just going to be a simple A to B first order reaction right here. So A is going to be getting converted into B right there. A nice little chemical reaction, simple. And basically what we have around the outside is a cooling system that is going to be manipulating the temperature within the reactor right here, alright? So basically what we're going to be looking at is we are going to be changing the temperature of the coolant around the reactor right here, and we're going to be looking at how that affects the concentration of A within the reactor and how that affects the temperature within the reactor itself, alright? So we are going to have one independent variable, which is going to be the reactor temperature, or not the reactor temperature, excuse me, the coolant temperature. And we are going to be trying to use differential equations and material and energy balances to find the concentration of A and the temperature within the reactor right here. All right. So the first equation that we're going to be used to try and solve our differential equations that we're going to be later coding into Python and actually solving this and graphing this out and seeing how the relationships work out is the Arrhenius equation, right? And the Arrhenius equation is written as K is equal to AE, and that is going to be all over, I'm trying to think here, I think it is negative EO over RT, if I remember correctly. So that is going to be all over that. And in this specific problem, we are given A as a KO, so we're going to go ahead and write that as KO right there. There we go, and there is our Arrhenius equation right here. Alright, so we did make a small little mistake in our Arrhenius equation over here. It is actually EA for activation energy and not EO. So there we go, we have negative EA right there. And basically what this Arrhenius equation says is this K right here, that is the rate that this reaction is going to occur, alright? So we have our, over here, this negative EA is the activation energy needed to go from A to B to get this reaction started. And as you can see here, since this T is in the denominator of this exponential expression right here, basically what that says is as T gets higher, this expression over here is going to become higher, which means the rate is going to become higher, and there's going to be more reactions going on. And that makes sense because we know that as temperature increases, the particles are going to be moving around, alright, and they're going to have more kinetic energy, and they're going to be moving at a higher velocity, which means they're going to be banging into each other a lot more, which means we're going to get more reaction going on, alright? The rate of reaction is going to be going up, and that is this K right here. That K represents the rate of reaction as we go from A to B right there. And basically, we can write out this as R equals K A right here. Alright, and this is the rate, and this is the rate constant right here for A right here, and that is going to be our rate equation for the rate at which this reaction occurs right here. Alright, so now we're going to take a look at the rate of the heat transfer that's going to occur between the reactor and the cooling system, alright? So we know that heat is going to transfer from the hotter part to the cooler part, right? We all learned that in thermodynamics. So the heat is going to be transferring down this way, like so. It's going to go from the reactor to the cooling system, all right? And we are given a rate constant for this within the word problem that we're going to be taking a look at later. And that rate constant for this heat transfer is going to be UA right here, all right? And we're going to be using an equation to solve for the heat transfer between these two systems, all right? And we're going to note that equation with the letter Q, all right? And this heat transfer is going to be equal to this constant right here, UA. And then that's just going to be multiplied by the temperature difference between the heating system and the cooling system, all right? So we're going to go the temperature of the reactor minus the temperature of the cooling system. And that right there is going to give us our heat transfer between the two systems. And now we're going to go ahead and get into the differential equations that we're going to use to solve for the concentration of A and the temperature of the reactor. Alright, so the first differential equation we are going to be solving for is we're going to solve for the concentration of A as it relates to the change in time. And to do that, we are going to be doing a material balance equation. And that is going to be the accumulation of A, that is going to be equal to the amount of A coming in to the system through this pipe right here. It's going to be equal to N, and then that's going to be subtracted by the amount of A going out of the system through the other pipe, in minus out. And then there's also going to be some consumption of A going on within the reactor over here because A is going to be getting turned into B. So we do need to account for that. So we do need to subtract it. So it's going to be in minus out minus consumed. There we go. That is going to be our material balance for A right there. And basically what we can do now is we are going to solve a differential equation. We're going to be putting some letters that are actually within the equation or in the problem to this equation right here. And basically what we're going to do is we're going to solve for the differential equation dCA over dt over here. And we do need to do the concentration of A as it changes to time because we are not given a specific mass for A. We are only given a concentration. And to get the accumulation, that is going to be just in mass. So we do need to change this. We do need to multiply this by the volume. That is because concentration is in moles per liter, right? And we want to get rid of that per liter so we can just get the moles because accumulation is just a mass, all right? It's not a mass per liter. So to make the units right, we do need to multiply this by the volume. This is just going to give us moles on this side, right? That's what we want. That makes the units all match up. And then over here, we are going to solve for the in minus out over here. That is going to be pretty much, we have this flow rate, Q, within the problem, right? Q is the flow rate going in and out of the pipes over here. So we are going to have Q times the concentration of A going in, and that's going to be subtracted by the Q times the concentration of A going out, all right? And since this is a well-stirred system over here, the concentration of A within the reactor is going to be the exact same thing as the concentration of A going out. So instead of saying the concentration of A going out, we are just going to use the concentration of A within the reactor just to simplify things and not add one more variable to it that we don't need. So for this in minus out right here, we are going to go ahead and do Q. And then we're going to do CAN minus CAR. CAN minus CAR. And then we're going to factor the Q out right there because the Q is the same one for going in and going out. So we can just go ahead and factor that out, make our lives a little bit easier. And then we are going to need to also subtract the amount of A getting consumed within the reactor, which is just going to be a factor of this K over here, the rate that the reaction is going to be occurring, right? So we're going to go K times the concentration of A, right? And then we are also going to need to multiply this by the volume of the reactor again, just so we can get our units all matched up. and get everything working the way we want it to. We don't want any missing units, and multiplying by this volume over here is going to get this all squared away. And yeah, and basically what we're going to do now is we're going to divide this whole thing by volume so we can get the derivative of concentration of A over the change in time, because that's going to be what we're doing in our Python. We're going to set this equal to this over here. We don't want two things over here on this side of the equation. So we're going to go ahead and go dCA over dt. That's going to be equal to QV over CAN minus CAR. And then those V's are going to cancel, so that's just going to be minus KCA. And there you have it. That is going to be our differential equation. And we're going to solve for the concentration of A. And now we are going to be solving for our differential equation for the temperature within the reactor. Okay, so now the next thing that we need to do is we need to come up with a differential equation that is going to allow us to solve for the temperature within the reactor as the temperature in the cooling system is going to be changing. Alright, and we're going to do that using enthalpy, alright? And enthalpy is written out as change in H, alright? And that is going to be equal to the mass of the compound times the specific heat C of the compound, and that is going to be multiplied by the change in the temperature. And since we are not given mass in this problem at all, we are going to be using the concentration again. And if you remember, mass is equal to concentration times volume. And we are going to be using rho to represent our density. And then we're going to multiply that by volume. All right. And there we have it. We could go ahead and plug in density times volume for our m right there. And that is going to give us our equation for the change in enthalpy. All right. And now we're going to be doing a balance pretty much like we did in the last one, where we did the accumulation is equal to the amount going in minus the amount going out minus the amount consumed. And we're pretty much going to be doing the same exact thing for enthalpy. All right. There's going to be enthalpy coming in, enthalpy coming out. And we're going to go ahead and write that out right now. All right, so we're going to go ahead and write out the left side of the equation, which is pretty much just going to be this right here. All right, we are going to have, we'll go ahead and do it over here. This one's going to get pretty long over here. So it's going to be PV times the specific temperature. And this temperature is going to be changing, all right? So that is going to be the change in the temperature of the reactor as it relates to time. So it's going to be D times the temperature of the reactor over the change in time. We'll go ahead and make this a capital T over here so that we don't confuse and think this is change in time. This is change in temperature over here. Alright, and that's going to be the left side of our equation. And now we're going to be looking at all the different factors that are changing enthalpy. Alright, so we have an enthalpy coming into the system. That's going to be subtracted by enthalpy coming out of the system, right? And then there's going to be enthalpy that is going to be lost as temperature is flowing from this hot compounds in here into the cooler compounds outside in the cooling chamber. So enthalpy is going to be lost during that. So we're going to go ahead and subtract that enthalpy. We'll call it HT since it's the temperature going out into the cooling system. And then we also have this exothermic reaction here as A goes to B. And so that is going to be causing heat to be lost, all right? So we're going to go ahead and add that even though it's being lost because the enthalpy of the reaction is negative. So we don't want to subtract by the negative because then that would be getting added. So we're going to go ahead and add the negative. So we're going to call that the enthalpy of the reaction right there. Enthalpy of reaction. And yeah, that is going to be our energy balance equation right there. Now we're going to go ahead and start adding some of these letters and variables into this so that we can apply it to our Python code that we're going to be using to model this later on, all right? I'm going to go ahead and erase that. Alright, now we're going to go ahead and look at the enthalpy in minus enthalpy out over here. And those are both going to be determined based on the flow rate. And the flow rate is going to be the same going in versus going out, so we're going to go ahead and factor that out. And that's also going to be multiplied by the density and the specific heat over here. So we're going to go ahead and do the density times the flow rate Q, which we used previously, and that's going to be multiplied by the specific heat of the compound, right? And that is going to be multiplied by our TR minus TC again. So it's going to be the temperature of the reactor over here, and that's going to be the TR going in up through here, and then we're going to have the temperature of the reactor going out over here. But as you know, since this is going to be well stirred, the temperature going out is going to be the same as the temperature within. So we're just going to go ahead and leave that as TR. We don't need to further write it out as TR out, since it's going to be the same thing. We're going to go ahead and put that in parentheses, and that's going to be our expression for the enthalpy in minus the enthalpy out. And now we're going to go ahead and write our expression for the enthalpy that is being lost going out into the cooling system over here. And that was pretty much written out right here as our Q. We already pretty much did that. That is going to be the energy lost to the cooling system right there. So that's going to be minus UA, and then in parentheses TR minus TC right here. There we go. And now the only thing that's left is going to be the enthalpy that is going to be lost due to this reaction up here, alright? And to do that, we're going to go ahead and add, even though it's going to be negative in the end because we have a negative change in enthalpy of reaction, right? This is going to be the energy that's being lost every time this reaction happens up here. And now what we need to do is we need to quantify how much the reaction is happening, right? And to know that, we are going to be multiplying this times the volume times the concentration, right? Volume times the concentration, because that is how much of the compound A is going. And then we need to know the rate at which this is going to be happening. So we're going to multiply by K, and that is going to give us the enthalpy that is lost due to the reactions, right? Because we have the amount of mass of A, and then we have the rate that it is being reacted with, and the energy change per reaction. So that is going to give us our enthalpy change for the reactions, and this is going to be our entire expression over here for the reaction, right? Alright, hello everyone. We have now jumped into our Python code over here in Colaboratory, and we're going to go ahead and set up some code so we can model our problem over here. I've gone ahead and written out the problem over here. Not written, I've copied and pasted it into this Google Doc over here, as well as the equations we're going to be using to model this over here. As you can see, we have our Arrhenius equation and our differential equations for the temperature within the reactor, and then the density of A within the reactor. And so now we're going to go ahead and get to coding. As you can see, I've already gone ahead and imported all of the systems we're going to be using, as well as all of the constants and factors we're going to be using within these equations over here that are given to us in this table. So yeah, what we're going to go ahead and do is we are going to find our RHS function, which is going to be the right side of our solve IVP, which is going to be solving our differential equations for us so that we don't have to go through and do all the math for it. It's going to make our lives real easy. And we're going to do our independent variable is going to be time, so we'll go ahead and use t. And then our dependent variable is going to be y over here. And we'll go ahead and unpack our dependent variable, since it's actually going to be two different things. It's going to be the density of A and the temperature within the reactor over here. So we're going to go CA and TR are going to be equal to Y. And then we're just going to go ahead and return our differential equations over here because that's what we're going to want it to go through and solve. So first we're going to do this one, then we're going to use a comma, and then also return this one over here. So we're going to return both at the same time, and we'll go ahead and cut to that now so you don't have to go through and watch all of that. Alright, we are back now. We have gone ahead and added in our return equations over here. As you can see, we have our first differential equation, the right side of it over here, then the comma, and then we have our third differential equation right here. And now what we're going to want to go ahead and do now is we are going to need to solve for k over here. Since we do have k is involved in both of these, and we do not have it defined yet because it's not going to remain constant, is going to be changing along with the temperatures. So we're going to go ahead and go k is equal to k naught, and then that's going to be multiplied by np.exp, which is going to be this e to the power of function over here, and that's going to be our e over r over here is actually a constant given to us already, so it's going to be our constant over t. And we have our constant written out as ER, and then we'll just go ahead and divide that by T. That's going to be our temperature of the reactor right there. And there we go, we've now solved for K. So everything is looking good over here in our RHS function. Let's go ahead and make sure that's running right. We'll go ahead and run everything else just to make sure that we have. Alright, the next thing we're going to want to go ahead and do is we're going to want to include our solve IVP function. So we're going to want to solve IVP, and then what we're going to do is we're going to go RHS, since that's the function that we want it to solve, and we're going to go over the interval 0 to t end over here, which is going to be the amount of time we're going to run this for. And then what we're going to do is we wanted to solve for using our initial density over here, our CAO, which is the initial density of A within the reactor, and then it's also going to be using the initial temperature within the reactor, which we have as TRO. Alright, we'll go ahead and get brackets around that. And we're going to be using the Rodau method again. So we're going to go method is Rodau. Believe that's how you spell it. We might have to come back to that in case we misspelled it. And then we're going to make our dense output is equal to true for this, like so. And then we're going to go .sol, so it solves it for us. And then we're going to go ahead and give this a name that we can call later on. And there we go. Let's see if that's working good. There we go. Alright, and now that we have our function over here, and then our solve IVP solving it for us at each specific time that we're going to specify later, we can go ahead and get to graphing, alright? And first, before we get to graphing, we are going to want to get our x-coordinate all laid out. So we're going to be doing a linspace for that. So we're going to go tplot is equal to np.linspace. And we're going to go from 0 to our end time over here, t end. And then we'll go about 500 data points. So we'll have 500 points evenly laid out between 0 and 40 right now. But we could easily change this if we ever wanted to. There we go. So that's running good. Alright, and now we're basically just going to want to put in our CA and TR into our solution function using these new time plots. So we're going to go solution using tplot, so it knows to solve the solution, our solve IVP function, for all of these different time periods, so we can get the data points going correctly. Alright, there we go. Alright, and now we're ready to get to graphing. Alright, so we're going to be making a graph with two different subplots within the same graph, so we can look at them side by side and not have to go through and do this two separate times. And it's going to make our lives easier, so we're going to go fig equals make subplot, and let's get the S on there so we don't forget that. And we're gonna have columns and rows in this one. So the columns is gonna be equal to 2, and the rows is gonna be equal to 1. There we go, and then we're going to add some scatter plots. So we're going to go fig dot, we want fig, not dig, fig dot add scatter, and then the x is going to be equal to our t-plot, x equals t-plot, and then our y for the first one, we're going to go ahead and do our CA over here. So we're going to go y equals CA. And then the mode is going to be lines. And then we'll go ahead and put this one in row 1, column 1. And then we'll go ahead and name this one CA so that we don't get these two mixed up. So we'll go CA. And that should do it for the first one. And we'll go ahead and copy and paste this one down. And just replace the CA with, don't want to pull up the dictionary here. Let's get that out of the way. Go ahead and copy paste that on down. And then we'll just go ahead and put in our temperature of the reactor and for the y coordinate and for the name so we don't get those mixed up. And we'll see what this is looking like, see if she's working all right. Oh yeah, we forgot to change up the column here. I believe, yeah, we had 2 columns, so we want this to be column number 2. Hopefully that's working all right now. All right, there we go. That's looking nice and dandy for us. All right, so we did make one small mistake in our coding up here. In our K equation, we did want to include a negative over here. As you can see, there's a negative in the exponential function that we forgot to include. That was messing with our graphs. This is not what we want it to look like. So we'll go ahead and get that negative in there. Then we'll see what this is all looking like. All right, let's see here. And here we go. This is what she's supposed to be looking like here. As you can see, the density of A is going to climb up very quickly and then kind of level off up here. And then the temperature within the reactor is going to be falling off and then bouncing back up a little bit, then stabilizing out. And that is for the case when the temperature is going to be 290 up here for our TC. But we also have one where it goes from 300 to 305. So we'll go ahead and look at that case right now. So we'll go 305 for TC, and we'll take a look at what that's looking like in our graphs. And as you can see here, we got a lot of funky stuff going on. All right, so initially, it looks like the density of A is going to be dropping off real fast, and we'll go ahead and we'll lower our TN just so we can get a better view of this. See what's going on a little bit better, get a better view of it. All right, and we can still probably drop that down a little bit more. All right, here we go. As you can see here, the density of A is going to be starting off at 0.5, and it's going to suddenly drop, all right? And then it's going to bounce back up. And over here, the reactor temperature is going to be kind of doing the opposite. So it's going to be kind of doing an inverse relationship between the two here, all right? As you can see, as the temperature of the reactor jumps, the density of A is going to be declining, and it's going to be keep going up and down as time goes on, but in the opposite direction for both of them. So they're going to be bouncing back and forth in the opposite direction, kind of, sort of. You can think about it like that, all right? And yeah, that's going to do it for today's video. Make sure to smash like and subscribe. I hope you guys enjoyed the video and learned something new today. And yeah, if you have any questions, be sure to put it in the comments, and I'll see you guys in the next video.